Log on, tune in, find out. Another good idea from Cambridge.
This morning is Ivona Grzegorczyk, who will talk on vector bundles of rank 2 with 4 sections on algebraic curves.
Okay, so I would like to thank you, Newton Institute and Professor Neustadt for inviting me here. And as you see, the title is kind of specific. I mean, I like specific bundles and specific number of sections, but I will give you sort of an overview what is happening. And there are a lot of developments that happened really in the past few months. So I will try to get there and sort of summarize everything. So our setup is the standard setup for Brill-Netter theory. So we have smooth, irreducible curve, vector bundles on it. N is rank of F. K, I usually denotes number of sections. D is the degree of F. Now we have these two invariants that actually made the idea of studying the problem independent of rank. So we had mu is degree divided by rank, and k divided by n would be lambda. And this actually let us make a nice picture for the problem to study. And M and D is a moduli space of degree D, rank n stable bundles. As we talked yesterday or the day before, we had a construction that came from Narasimhan Seshadri a while ago, and this is the one we're still using. So I'm using also the standard definition of the stability. So bundle is stable if any subbundle has a smaller slope, or semi-stable if we're allowing to be equal. Okay, now really the interesting part is when rank is bigger than 2, bigger than equal to 2. And so we have our moduli space, and actually the moduli space for semi-stable bundles is actually not the same as a moduli space for stable bundles. And we have nice, actually, nice situation, because our moduli space for when n and d are coprime is actually a very nice variety, which is of the very easy to calculate dimension as well, and square g minus 1 plus 1. Now, what we really want to study are subvarieties in it. So the subvarieties we want to study are bundles with a prescribed number of sections. So if, whoops, that's not what I wanted. Okay, if we want k sections, and we would like to have bundles stable, or we want k sections and we want bundles at least semi-stable. So the difference is usually you put the bar or you put tilde over it. So whichever, I will have a collision of notation at some point, because I use pictures and the pictures use old notation. But I will warn you when I get there. Okay, so the biggest question is if it's empty, and if it's these varieties B's are empty, not empty, then we have expected dimension, okay, which we can calculate as well. Now, old notation was using rho for this formula. New notation is using beta. So again, I'm warning you, it may happen that I have both. And we can actually figure out what is a tangent space at a given point that's a bundle in the space, and it's given by Petri map, and it's actually a good way to think about smooth points on the variety. If this map is injective, we're getting a smooth point. And if not, that is a singular point. However, this is not really a big restriction on the curves we are studying, because all general curves, whatever it means, they actually satisfy Petri condition. And also there are some curves on K3 that satisfy this condition. and there are possibly others. Now, nice thing also to know is that the singular locus of this varieties is a variety of one dimension bigger. Now, when we look at the case when rank is 1, it's completely resolved case, but it actually does what one expects the situation to be. So Abarella, Cornaba, Griffiths, and Harris resolved the whole case. Everything is well understood. The non-emptiness is well understood. Dimension, calculation, reducibility, smoothness, they are not empty when they're not supposed to be empty. These Brill-Netter varieties. These B's, or sometimes we call them W's. Now, when B and K is non-empty, we're getting some special embeddings of curves. And then, well, we use it today a little bit. And also, emptiness or non-emptiness generates some sub-varieties in the moduli space of curves. That's why the whole thing is interesting. Now, Brill-Netter problem, it's really formulated for higher rank. So, the questions in here, the standard questions are, is this variety non-empty? And this is not completely answered yet. Is this connected? If connected, how many components? If it's irreducible, what are the components? What's the dimension? Does the situation follow the expected dimension? What are the singular sets? And does B and dk depend on the curve? And that's sort of what is happening right now, that it turns out that in many cases a lot. Okay. Now, so in case when rank is bigger than 1, the variety of vector bundles of specific degree depends only on genus of the curves. However, the Brill-Netter theory looks like it depends on the curve. Now, general curve may have completely different properties than the special curves. And this actually, even though it is, we study subvarieties of bundles, you may generate, you're generating some nice subvarieties of modular space of curves that actually give you insight of the geometry of NG itself. So that's sort of a motivation. And let me show you some pictures, how we sort of visualize the whole problem. So if we use the variables mu and lambda, so we divide by rank, and we try to make a picture that's independent of rank, then we can plot our expected dimension, and actually we would want to plot this thing equal to 0, so this would be some sort of hyperbola. And the thing is to, in order to actually make it independent of rank, we had to -1, because then everything, all ranks go away. Otherwise, we'll have 1/n everywhere. The other thing that, so this sort of should give us the area that we would like to study. Anything that it's when this value is bigger or equal to 0 should be producing varieties, Brill-Netter varieties that are not empty. Now, the other things that we would like to put on the picture, sort of to reduce the region that we study, are the things that are known one way or the other. One is the Clifford band, and this is a Clifford band that is already generalized to rank n bundles. So this was done by Xiao, one of the definitions. And so if we divide this by n, we're getting the same formula independent of rank, right? Then we have Riemann-Roch theorem, which we also can divide by n. So we get the straight line that gives us the picture. And we also can use third duality, which sort of means that the degrees of interest, I mean the mu's of interest, are smaller than G-1. Okay, so if we go like this slowly, so here we have our mu, so this is really the degree axis, and this is the number of section axis, and we sort of try to narrow it down. So of course we're not interested in negative number of sections. G minus 2 gives us H1 equals to 0, so this actually piece, the yellow here would be coming from self-duality as empty. Then Riemann-Roch theorem, the, I don't know what you see, brown on orange piece, this is completely solved by Riemann-Roch theorem. So this is not interesting from the point of view of the Brunner theory. And this is Clifford bound, so there would be nothing here, nothing above. So this is sort of the area that we are studying. And in here we put this beta rho line. So expectation was that anything below the line would have a positive solution, so meaning there would exist a variety that's not empty. And then we try to calculate the dimension, which is hopefully coming from the prescribed formula. So the first result, which is from the late 80s, I believe, along these lines was Teixeira's parallelograms sort of description. I'm not quoting formula here because it's very complicated, but you, on the picture you actually see what happens. So generally, what she did under the curve, she was able to construct parallelograms that guarantee that the moduli space will be non-empty. The tricky thing was that whenever her coordinates ended up on the curve, she was able to produce only semi-stable bundles, not stable bundles. Now, in here, as you see, the problem looks like the closer are you to the curve, the harder the problem becomes. Right? So we like somehow would like to measure how far your bundles are from your curve. Now, the second, and in here again, I use W for B, for the Brunner locus. This is the old notation, but I did not redo the slides. So W's are B's. Now, the second sort of interesting result was the area where your 1 by 1 square. So when your slope is smaller than 1, smaller equal to 1, and when the number of expected section is smaller than the rank. And so in this region, Letitia, Brambilla, Peter Newsted, and I, we were able to solve the problem completely. And the problem actually showed that it's not exactly what we expected. This is not a piece of your hyperbola. This is actually a tangent line to hyperbola. So it means that the hyperbola actually goes a little bit above in here. So there was a region that you were supposed to have bundles and they don't exist. But in this region, actually, you're getting a completely positive solution, which means your bundles exist, they are stable, you were able to construct the component is irreducible, and it's of right dimension. As you see, this works everywhere except for 1, which means rank n and sections. Now, this was extended by Vincent Mercat, and he also got in this area, everything is perfect, the way we want it, except as you see in here, where you have only semi-stable bundles existing up to some point. That's a mystery as well, why is that? But that's what happens. Okay, so what I said is that our interest is really in the area that's very close to the Brunner curve. Now, we have Clifford bound, right? So that's a standard thing. But if we look sort of at the Clifford bound and try to calculate how far this expression is sort of measuring this new integer function, if we rewrite it in a nice way, we make it into integer function. This is sort of measuring how far is your curve, your bundle from the upper bound for Clifford bound. So we define Clifford index, so to speak. Okay, so we take a bundle, we take our numerical function, and we try to minimize it. Okay, and when we try to minimize it, then what may happen, for example, may happen that it's equal to 0. So it means actually they are bundles that achieve the Clifford bound. Now, this only happens on hyperelliptic curves. Now, also what may happen that they are very, very far away from your Clifford bound. And this apparently happens on generic curves. So it means on general curves, sorry. So if you have a lot of the curves that you would want to study actually are far away from the Clifford bound. So in order to get actually to produce bundles that are close to your raw, you have to consider some special bundles. That's what that says. So here you have sort of a picture of the situation. So if we take, we want the Clifford bound bigger or equal to 0. So this is this one is this one, right? Okay. Then if you want 1, then you're getting white, and actually they don't exist, but the curve in here goes somehow like this. Okay, up to here, between these two. And I mean, you use this Clifford bound, and you can try to go down with these lines, and then you're getting non-emptiness above these lines. However, what happens? The unusual thing happens because there are some corners. So you see this piece is the piece that came from this small slope consideration. So there is one line that goes for a while, and then you have another line, and this comes from duality, this piece. So really, we're interested up to genus -1. The rest is some dual through set duality. So in here, there are some corners. So for example, on this one, the possibility is that all the stable bundles exist on this line. They don't exist on that line, so what is happening in the corner? You're getting like two different messages, so to speak. So the idea would be to sort of try to see if we can produce some other lines maybe for higher ranks. This is Clifford index, so Clifford index has to do with line bundles. Now we really are interested in rank n bundles, so the question is, can we somehow get this idea going when we take rank into consideration? So we try to, many people try to generalize the higher Clifford index, and then this indices would be new curve invariance. Now there were a few different ideas, but apparently the one that was quite recently established finally by Peter Newstad and Langen is the following. So you see, it gets into consideration the rank. So you're taking this part, sort of coming from the Clifford, the old Clifford bound, but you're dividing it by 1/n. Now again, what's nice about it, that you can nicely formulate this condition using mu and lambda. So it means it's again independent on the rank. So what we get like a series of new indices for the curve. So curve comes not only with a Clifford index, but comes with a lot of different indices that sort of describe the property. But you see the thing also in the definition. I mean, this is the gamma, and now I want to minimize it. But the condition that we put on here, this is sort of the part that's important. Its question was what to put in here. And there were different ideas, and actually asking for double rank number of sections is it. It looks like it best describes the situation. And so as you see, you can describe nth Clifford index in this way using mu and lambda. So again, I can go back to my picture and get these lines on them. And actually, I don't have a new picture for this situation because it looks very much like an old picture. These are really lines with slope 1/2 that go down a little bit. The previous ones were going all the times by 1/2 down. Okay, 1/2 of the unit down. But this one sort of corresponds to the line bundle situation. So now the question would be, if your locus is above these lines, are you empty or not? Now, look, this definition, as stated, it's actually generalizing the usual Clifford bound. So it also fits very well with the old situation. So it looks like it's very, very nice. And the very next thing, we had...
Just a minute.
Uh-huh.
Is it lambda or 2 lambda?
This one in here, lambda. It's lambda. Yeah, sorry. Yeah, always titles. I double check, but yes, thank you. So after we define all these very nice invariants, suddenly we have a conjecture that they are all equal. So it means, well, if they are equal, what's the point? Right? I mean, we don't want the indices that they are all together the same. So the thing is that this is not actually the case. So what are the examples at the moment? And these examples, most of these examples were generated in past few months. Okay, so actually it happened after reformulating the definition of Clifford index. Once we reformulated Clifford index, that certain examples came coming. So for example, if you are on arbitrary smooth plane curves, so then this holds. General k-gonal curve. I will tell you what k-gonal means, but it means that line bundles have certain number of sections. That there exist line bundles with at least 2 sections for certain degrees. Now, for a general curve in M11, it works, which is very interesting example, and that's done by Farkas and Ortega recently. And it works for all Clifford curves of genus smaller or equal to 4. Now, it fails. Okay, there are cases that it fails. So it fails when when you actually get Clifford index maximum, and it actually happens that gonality is maximum at the same time. That's some sort of a consequence of the calculation. So there are examples that Clifford index is 5, but second Clifford index is smaller. And this happens on some curves on K3. And again, this is in case genus is 11. So it looks like this 10-11 case is going to be special. Now, it also fails in rank 3, which I'm not going to deal with, really, but there is an example when your curve is also maximum Clifford index, but gamma 3 is smaller. And it works for curves of degree 9, 11 or higher. Genus 9, 11 or higher. And again, they end up on K3. And these are actually examples, again, of bundles with 4 sections. So as you're seeing, this is where...
Bundles with 6 sections.
6 sections, yes, sorry.
And this is it works on general curves of genus 9 and 11. Whereas the other examples, the rank 2 examples, only work on special curves.
Right. These ones are specific ones that we need to construct. Now, general question is again here, which is not clear at this point. Is this the consequence of the fact that the curve has a maximum index, Clifford index, or is this connected to the fact that these curves are on K3, especially for the second one, or rank 2 case, or in rank 2 case, is it just a special case? Now, the other sort of set of examples come from bundles that have prescribed determinant. And these ones are sort of the ones that contradict what we would like to have in Bruno-Latour theory in many cases, because first of all, B2, this is the canonical divisor, it's usually empty on generic curve, but it's not empty on curves of, that are on K3. So on special curves, it's not empty, and on a general curve, it is empty, general here. Now, also, there's a way to calculate the dimension of the component if it's not empty. And, you know, Bertram, Feinberg, Mukai started calculating it. Now, Osserman has some generalized calculations for some bundles with fixed determinant. So actually, they do not coincide. This beta is not really our original beta. So in here, what we get for, maybe we should use actually a different notation in here. This is expected dimension for the Bruno-Latour locus, but this is not the expected dimension that we calculated before. And they actually, in general, this our beta is smaller than the beta that expected for canonical bundles. So here,
This thing is larger K rather than small.
larger K, yeah.
I think it's correct for small values of K.
For small,
It's ones that are close to the possible limit. That it's
right. Okay, so once we started doing the invariants, then why stop? There are other invariants that may be of value. And this is the gonality. I told you I will tell you what it is. And this actual idea was around for a long time. People studied it. So this is not really new. What's new is sort of formalizing it in some sense. So what dr is, this would be sort of gonality, Rth gonality of the sequence, is we minimize the degree of the bundle that has R+1 sections. So in general, I mean, for example, you can calculate D1. These are calculations on the Petri curve, but you can calculate these numbers most of the time for a lot of nice curves, and this is very closely related to Brill-Netter for rank 1, right? Because we have very nice results for rank 1. So by classical Brill-Netter, we know that this degree has to be smaller. This is the expected degree coming out from the fact that the locus is not empty. And we prove that on Petri curves, actually you're getting the highest possible gonality. So, and Petri curves are sort of general curves, plus some stuff, right? Plus some special curves. So this is sort of like a general case that you would like to study. And you actually have this, you actually have this dr. Now, so it turns out that for rank 2, D4 is of interest. So D4 is the degree of the bundle, smallest possible degree of the bundle, that the bundle will have 5 sections, right? And again, if we look at the Petri curve in here, then we can calculate all the indices that we had defined, and they come out nice and easy. In here, they're all integer. And we'll concentrate more or less on this case. So now what I want to do, go back to what we start with and look at the rank 2 bundles with 4 sections. And the interesting case would be when genus equals to 10. And why is this case altogether interesting at all? First of all, expected dimension is smaller than 0, so you expect that they will not exist, bundles like this. I mean, at least stable bundles. In particular case, I mean, we already showed that the case when rank is bigger than 2, especially with the new examples that around 10, this situation is not a consequence of the classical Brill-Netter. So that you will be producing something new. Now, also Mercat's conjecture in this neighborhood. So this is sort of for Clifford index, if you calculate it, it's smaller or equal to 4, it has counterexamples in there. So in this neighborhood in the Brill-Netter locus, you have counterexamples for existence. And there are new examples from Farkas and Ortega for genus bigger or equal to 10. So it's sort of like nice thing to study, and this is sort of the first case that nothing was known. And so what I will do from now on, I will report on the work that I did with Peter and Vincent Mercat. Okay, so this really gets to resolve this particular case. Now, when this genus equals to 10, then Clifford, we can calculate Clifford index is equal to 4. But what's interesting is I will look at the degree 12 bundle. And actually here, when we calculated the, I calculated here the gonality, different gonalities. And if you notice, D1 is 6, D4 is 12. So I would be sort of looking at the connection between D1 and D4. It turns out that that's an interesting part. And if you look at the sort of the Clifford inequalities, this point is this corner that I was mentioning before. So it's actually not clear which way it should go. Should they be empty or they should not be empty? And you know, when dimension, expected dimension is actually negative, so you would hope they don't exist. Now, so we resolved this problem completely. So the theorem is the following. If C is general, then there are no bundles with rank 2, degree D, and 4 sections, if degree is bigger than 12. Even though the expected dimension is positive.
Are you saying there are bundles? It's not empty.
It's not empty, sorry, they are
It's
bundles.
the expected. It's the expected.
Sorry. Yes, but the degree is 12. Yeah, well, I wanted to say, I wanted to consider in degree 12. Right, if degree is bigger than 12, this is not empty. Okay, now what happens when degree is 12? Okay, and this is degree. Okay, this is degree. So then in degree 12, there exists a curve that actually has vector bundles that are stable, and actually expected dimension in this case is negative. This is a D. Okay, in here. So where is all this coming from? So I'm not sort of going to show you the entire proof at lots of calculations and so on, but I will sort of give you an idea how we approach this problem. So first of all, for genus bigger than 2, we sort of divided the situation into 3 cases. And again, we compared D1 with D4. So D4 means that there exists a bundle with 5 sections, and D1 means that there exists a bundle with 2 sections. And actually, I don't know if I did sort of spend time on explaining this gonality, but gonality is sort of increasing. It's an increasing sequence, so to speak. And in here you would expect, especially for multiplicities, that that it would jump up. Well, so what happens? I mean, the situation very much depends on the fact if your curve has one bundle or more, not isomorphic bundles that have at least 2 sections. And there are a lot of curves like the ones that do. And if your curve has at least 2 bundles that are not isomorphic, then we can construct certain extensions of these bundles by two vector bundles, and we can prove that the semi-stable are not empty if your degree is bigger than 2D1, so twice gonality, and stables are not empty if your D is bigger than 2D1 plus 1. So this one's sort of getting you closer to the curve. If only one bundle exists, then there is a problem, of course, but there is a way to overcome it, and so the only thing we cannot claim is that 2D1 plus 1 and 2D1 plus 2, if your bundle wants to have degree equal to 2D1 plus 1 or 2D1 plus 2, that these ones are empty. They may or may not be empty. Okay, it's not clear, I mean, from the calculations. Now, what may happen also is that you have equality. Then this really is similar in a resolution, in a construction to case 1, but if your bundle is of double gonality, it's possibly could be already non-empty. So you may have a stable bundles of degree 2D1. And once this happens, you get non-empty stable bundles for degrees bigger than 2D1. So this not sharp inequality becomes sharp. If this happens, that this one is not empty, that's a conditional statement. And then in a case that you have your D4 is smaller than 2D1, then we look at the minimum possible degree that gives you a stable bundle. And if bundle like this exists, it has to be, first of all, between D4 and D1, 2D1. And in these two cases, if 2D1 is bigger than minimum, then we get very actually nice solution that stable bundles exist for D bigger than the minimum. And if they equal, actually this gets us back to this case. And depending on emptiness of this locus, we're getting non-emptiness for 2's bigger than 2D1. So if this one is non-empty, we get this one non-empty. So actually we don't produce this for sure. So just to sort of give you an intuition, what is happening. So let's look at the Petri curve. So you will get the feeling for what it is. So at Petri curve, we actually know how to calculate the gonality. So for example, if genus is 4, 6, 8, this gives you, this puts us in the case, first case, and gives us non-empty locus for D bigger than 2D1. And in here, see, if you calculate D1 and D4, this is the area where your D1, when your D4 is smaller than twice D1. And this is the area where your D1 times 2 equals to D4. And everything below that would generate the third case, when D4 is twice D1 is bigger than D4. But you see, it comes out, it looks like there are actually a lot of cases when they are equal. And that's it, that's an example. Okay, so the other example, sort of what is happening in this situation. So if we take a curve that has dimension, Clifford dimension bigger than 3. And Clifford dimension bigger than 3, it means that if I calculate D1, D2, D3, and try to use them to calculate Clifford index, they will not compute Clifford index. So to compute Clifford index, it means that you are the minimum. And so it means that I need D4 actually to calculate Clifford index. So at this case, we can actually calculate the D4 from the Clifford formula for the Clifford index. And it comes out that D4 is smaller than twice D1. So this puts us in case 3. So depending on the on certain things, depending on if the conditions are satisfied, you're getting non-empty locuses. Now, if actually if C is of dimension 3, so D3 calculates that, then C can be embedded, can be embedded into P3, and actually it's an intersection of two cubics, and this was done by Martens a while ago. And again, you're getting the degree and degree equal to 12 in here. So in this particular case, actually what we do, because this locus is not empty, so by the star we actually getting all possible 2D4 non-empty when degree is bigger or equal to 13. Because the condition in there was that the previous one has not to be empty. So you have, from Martens' construction, you have this condition satisfied. And now, the other easy calculation gives us the following properties of the bundle in this particular situation. So if our bundle is of degree D4, so again we are in rank 2 and we would like to have 4 sections, that E actually has exactly 4 sections. We can calculate the number of sections for the determinant bundle, and it's 5. And E is generated. So bundle is generated by its global sections. So in here. Because of this first 3 conditions, we actually have a canonical morphism from from lambda to H0 E to H0 determinant, and this morphism is surjective. So I'm not going to again to prove that, but that's sort of a useful thing that we will we use in the construction. Now, if D4 is smaller than 2D1, then in our trichotomy, we are in case 2nd or 3rd. Now, what happens then? That if we have a bundle, not the other way. Where are we? In here, okay. If we have a bundle that's not empty, then we have a line bundle in of the same degree with 5 sections, and this bundle gives you the embedding that's contained in the quadric. So this is the statement. Sort of under these conditions, we can actually, if we have a bundle in this locus that has 4 sections and degree D4, we can embed our curve as a quadric into a projective space. If the degree is smaller than 2D1, then there exists the bundle. Yeah, then exists the bundle. Then exists the embedding in a quadric. This embedding actually will generate a bundle that shows that B2D4 for it's not empty. And sort of how does the construction go? This is sort of a standard construction that we take. So we look at the case A. So we have a bundle with 4 sections, and it's generated by the previous statement. In this case, it is generated, so I can use the sections to embed it in a Grassmannian to 4. But then when I can embed Grassmannian into P4 as well, into P5, sorry, in this case. So here I have this canonical embedding that is given by the sections of this bundle. Now, on the other hand, I can look at the determinant of the bundle, and this one will be also generated, and we'll have 5 sections. So it means that I can embed this curve using this map into P4. Now, I have a canonical map from lambda square H0 of E to lambda h0 that e. So I have a canonical embedding going from P4 to P5. So where is my curve? My curve is an intersection of this Grassmannian in P5 with a hyperplane coming from this canonical embedding. Now, to do B, we actually use this bundle, existence of this bundle that has 5 sections that defines the quadric to construct stable bundle E. So this way we show that D4 is not empty. Okay, so this is sort of the summary of the proof, how the whole proof will go with all these helpful things. So there, in this situation, when genus is exactly 10, degree D1, so gonality is 6, and D4 is 12, we have a lot of vector bundles that are not line bundles that are not isomorphic, and they are of degree 6 with 2 sections. And this comes from old calculations by Castelnuovo. As far as I remember, there are 42 different isomorphism classes. So this one's there is no issue. So it means that we can actually use case 1 where we always assume that we need these bundles, at least 2 bundles with given number of sections. So, already we showed that if degree is smaller than 12, so in our case this is D4, then B2, D4, 4 is not empty. And otherwise we know that this is not empty for D bigger, it's empty for D smaller than 12, and it's not empty for D bigger equal than 12. So now let's look at our particular case. So when D is equal to 12. And again, what we do, we use the embedding, we take the bundle, we use the embedding into a quadric. And then we sort of looking at this quadric and looking at the sections of the M, which is the bundle. Oops, this is L and M is the same here. M is the bundle that I use to embed my curve into a quadric. And it turns out that this map in here, it's not neither subjective, it's not injective nor subjective. And that's sort of a tricky thing because it means from what Voisin showed that it has to be for a general curve. So it means that in this case, it cannot happen when the curve is general. Okay, curve is general, we cannot have bundles in this corner. Now, so let's forget about being general and just look at the curve that is on the K3 surface that generates Picard group of the surface. So for genus even equal to 10, it's an even case. So we have Voisin construction, and she shows that again this map in here it's neither injective nor subjective, but that implies that the curve actually ends up in a quadric. So you have a quadric, and you can get the normal bundle, and this will show that this construction will show that we're actually producing a bundle that is stable. We can calculate the fact that this is stable. The stability conditions at every stage, they are the hardest part of all these proofs, not the calculations per se. Now, however, what happens here, our expected dimension in this particular case, -3. So it means this is example of a bundle that goes against expectations of real network theory. That something that's you have expected dimension negative, and you're producing a bundle, although the curve is very special. And again, in this case, the curve is also on the K3 surface. So far, the only source of examples that are counterexamples are either they are connected to K3 surfaces. So again, it's not clear. Well, what's the thing to do? Well, there are issues of computing this Clifford indices for various curves, and trying to figure out which bundles will actually compute them. And there's an idea of something like a primitive bundle, which means that it's generated and its dual is generated. And they look like they are good candidates for computing the indices. Still, there's a need to construct components. If we know that the thing is not empty, there are actually not that many components that are constructed if you look at the entire pictures. Considering the situation when determinant is fixed, and actually Brian Osserman did like a generalized some calculations for expected dimension in this case. And his calculations are connected to, his determinants are really close in some sense to canonical determinant. They are completely new connections with Koszul complexes that are mostly done by Farkas and Ortega. Maybe there are some other interesting invariants that can describe the situation better in here. There is a whole new area of coherent systems that it's sort of building on Brill-Netter. And again, I mean, these ones are all of these ideas are connected to studying of geometry of moduli of curves itself. So I haven't seen much work done along this direction, you know, using Brill-Netter theory. And I think I'm like a few minutes ahead of time, but that's it. Thank you.
Any questions?
So, if I understood well, until now, all the examples where the expected dimension is negative, but the space is non-empty, are constructed for curves that lie on K3 surface.
Yes.
But I mean, is it expected that for general curves, the expected dimension is reached, and maybe the curves that lie on K3 surfaces are general for rank 1 Brill-Netter theory, but not for higher rank Brill-Netter theory, or is it expected that the dimension...
Well, you know, what expected, expected stuff is the stuff, you know, I showed you at the very beginning. So, you know, that what Brill-Netter theory really is all about, that you would, to start, expect that as long as curve is general, everything works. But so far, all this K3 stuff shows counterexamples. So they were constructed actually even before Brill-Netter was very well defined. Mukai's examples are very old. You know, so there is something special going on about K3 surfaces. And we actually don't know any other surface, so to speak, that would be special in the sense that curve ends up in some other special surface.
Could I make
Sure.
a comment on this? And that's as far as the having Clifford index less, the higher rank Clifford index less than the Clifford index. So in other words, counterexamples to Mercator's conjecture. This is certainly all the examples so far constructed lie on K3 curves on K3 surfaces. However, you can get negative Brill-Netter numbers for general curves. Well, you get them from this canonical thing. These canonical things can give you negative ordinary Brill-Netter numbers. So in the first place, it has something to do with the actual determinant bundle, or the determinant of the line bundle. Oh, sorry, the determinant of the vector bundle actually affects this question of the existence of things with negative Brill-Netter numbers. So there are examples there, but those are sort of can be explained, I think is the answer. There needs to be some change to the definition of the Brill-Netter number in talking about bundles with fixed determinant. That's one thing, but that's under control. The other things I think are not under control, basically, or we have lots of examples, but which use the structure of K3 surfaces. The Picard groups of K3 surfaces and what we know about them. But whether there are other examples is not Any more questions? Sorry. Anybody? Any more questions? Okay, so can we thank you very much?
Thanks.